Let's take a look at the answers to the assessment preview worksheet. A water balloon is dropped straight down from the edge of a cliff and travels for 4 seconds before striking a teacher who is standing on the ground. So let's make qualitative position, velocity, and acceleration graphs. Let's give this position graph a negative slope. We used to say a negative slope is going backwards, but we also know that a negative slope, when we're talking about vertical motion, means going down. But look what's happening to the slope. The slope starts out flat, and then the slope gets greater and greater. That means the velocity gets greater and greater, because on a position graph, slope means velocity. If the line was up here, the object would be traveling up. The line is down here, so the object's traveling backwards. And as time goes by, we can see the velocity is getting greater and greater. So this is going down, speeding up. To get your acceleration graph, look at the slope of the velocity graph. This is a negative slope, so we have negative acceleration. We have the same scenario now, and it says a projectile always has an acceleration of, you can say negative 9.8 meters per second squared. Now it doesn't matter if the object is traveling upwards or downwards, the acceleration is always negative 9.8. This negative sign doesn't tell you the direction of the velocity or the direction the ball is going, it tells you the direction of the acceleration that's acting on the ball. How far did the water balloon travel before striking the teacher? Well, that sounds like a kinematic problem. So let's write down what we know. A water balloon is dropped. So if it's dropped, we assume the initial velocity is 0 meters per second. We know the acceleration for a vertical situation like this is always negative 9.8. They give us a time that's 4 seconds, and they want to know how far did the balloon travel. That sounds like x, distance or displacement. So we have 3 variables, and our fourth, we have a question mark. So the thing that's not included in that list is final velocity. So we would use the equation that does not have final velocity in it. For acceleration, plug in negative 9.8. For time, plug in 4. For initial velocity, plug in 0. This 0 drops out. So if we square 4, we get 16. So now 0.5 times negative 9.8 times 16 is negative 40 meters. So what does this mean, negative 40 meters? Well, it means that this object had a displacement in the downward direction. It had a displacement of negative 40 meters. So that means that this balloon, we could say traveled downward 40 meters, or we could say negative 40 meters. A teacher who was standing in the bleachers drops a water balloon on a student who is under the bleachers looking for her phone. The water balloon is in the air for 0.8 seconds before striking the student. How fast is the balloon going right before impact? Well, let's list out what we know. The teacher standing in the bleachers and drops a water balloon. So that's starting from a velocity of 0. So it starts in her hand. The acceleration is always negative 9.8 in problems like this. We know the time, it's 0.8 seconds. It says how fast is it going right before impact? Well, that'd be final velocity. So we have 3 numbers. Our fourth is a question mark, and the thing that's not included is x. So use the equation that does not have x in it. Let's plug in what we know. Acceleration is negative 9.8, time is 0.8 seconds, and then initial velocity is 0. The 0 drops out, so the velocity is negative 7.8 meters per second. So what does that negative tell us? Well, the negative tells us the direction of the velocity. So in this case, the direction of the water balloon. So the water balloon is traveling down. True or false? When studying projectiles, even though there's only one object moving through the air, the horizontal and vertical motions of that object should be analyzed separately. Yeah, that's true. You're going to make a horizontal column and a vertical column. Now here's an interesting question. A bullet is shot horizontally from a gun. And at the same time, and from the same height, a bullet is dropped. Which strikes the ground first, the shot bullet or the dropped bullet? Why? So see what's happening? One bullet's being shot, and at the same time, another bullet is being dropped. Which one strikes the ground first? Well, it turns out they strike the ground at the same time, because once the bullet leaves the gun, there's no force other than gravity acting on it. Just like the bullet that's dropped has no force other than gravity acting upon it. So you got to remember here that the horizontal and the vertical motions of a projectile are independent of one another. What I mean by that is, even though the bullet is moving horizontally through the air, what's happening vertically is not related to what's happening horizontally. What's happening vertically is this bullet is simply falling to the ground. As it falls to the ground, of course, it moves horizontally, but those two motions are independent of one another. What do we know about horizontal velocity of a projectile? We know it's constant velocity. So V sub O is the same as V. And this is for the horizontal velocity only. The vertical velocity, of course, increases. A physics student throws a rock off a cliff at 12 meters per second. The cliff is 70 meters high. What is the time of flight, and how far away did it land from the base of the cliff? It says, hint, the rock is falling down and will have a negative displacement. Yes, we're going to need that information. So let's list out what we know. We need a vertical and a horizontal column. All of our problems, all of our projectile problems should be set up like this with V sub O, A, X, and T. Then we fill in what we know. We know the initial vertical velocity is 0. Because the moment it leaves its hand, while it's accelerating down, it doesn't have any velocity yet. Acceleration is always negative 9.8 in the vertical direction. And this is where we have to know that it's falling negative 70 centimeters, or 70 centimeters in the downward direction. And we don't know the time. We do, however, have 3 pieces of information, and they're asking for a fourth. Horizontally, we know the initial velocity is 12 meters per second. Acceleration, there is none, because remember in the previous problem we said the horizontal velocity stays constant. So if there's constant velocity, that means no acceleration. And we don't know how far it lands. That's what we're trying to figure out. So how long was it in the air, and how far away from the base of the cliff did it land? So now that we have 3 pieces and we're looking for a fourth, we can do a kinematic. We use the kinematic that does not involve final velocity, because there's no final velocity in this list. So plug in what you know, and now you can see we're going to have to solve for time. This 0 drops out. So we do 0.5 times negative 9.8. Now we divide both sides by negative 4.9. Now we have 14.3 equals time squared. We need to take the square root of both sides. So the time is 3.8 seconds. Once we get that 3.8 seconds, we can plug it in over here. And we know it's just one object. So when it hits the ground vertically, the object has stopped moving horizontally too. So it's also 3.8 seconds here. It's just one object, remember. So now we have 3 pieces of information and we're looking for a fourth. We can use the same kinematic. We use the one that does not have final velocity. Plug in what we know. Remember, the acceleration is 0. Initial velocity is 12, and the time is 3.8 seconds. So this 0 here is going to make this whole part of the equation drop out. So it's just 12 times 3.8. So the height of the cliff ends up being 45.6 meters, and the time it takes, or the time of flight, is 3.8 seconds. So these are our 2 answers we were looking for. A car with a mass of 1,250 kilograms drives off a cliff with a velocity of 13 meters per second. 13 meters per second is about 30 miles per hour. The cliff is 40 meters high. How long is the car in the air? That sounds like time. And how far away does the base land from the cliff? It sounds like height. Hint, you do not need the mass of the car. Yeah, we've thrown that in there to throw a little wrench in things. All right, same chart as always. Same variables, and let's plug in what we know. We know the initial velocity vertically is 0. Acceleration is always negative 9.8. Negative 40 meters, remember, because the car is falling down. It's going to travel 40 meters in the downward direction. That's what that negative tells us. And we don't know how long it's going to be in the air. That's what we're trying to find. They give us the initial velocity, it's 13 meters per second. There is no acceleration horizontally, remember, because horizontally the object continues at constant velocity. All right, we don't know x. Using this information, we can use the same kinematic, the one that doesn't include final velocity. We can plug the info in. Remember, we're solving for t. So this 0 drops out. We can do 0.5 times negative 9.8. Now we have to divide both sides by negative 4.9. Now we take the square root of both sides, and time is 2.9 seconds. We can plug that in over here. And it's the time of 2.9 seconds for horizontal as well, because we're analyzing one object. There's just one motion. All right, we have 3 numbers, and we're looking for a 4th. So you probably notice it's the same kinematic for all of these problems. Let's plug in what you know. Remember, acceleration horizontally is 0, so that causes this whole portion of the equation to drop out. So it's initial velocity times time. So the answer is 37.7. The object is in the air 2.9 seconds, and it travels 37.7 meters away from the base of the cliff.